This video is about determinants. We've got two objectives. We're going to define and compute determinants, and then we're going to prove some theorems that simplify the computations of determinants as well as the proofs of later theorems. Our first definition is a submatrix. So if I have this matrix A here, we define the submatrix, A with an I and a J in parentheses like this, to be this matrix A with row I and column J deleted. So the I tells you what row to delete and the J tells you what column to delete. This is what it looks like if we write this submatrix Aij in terms of the matrix A, where row I, which would be in here, is gone, and row J, which would be in here, is also gone. This is pretty complicated looking. It's a little easier to see how this works with an example. So here is a very boring matrix, A, little 4 by 4 matrix. A23, so the submatrix A23 with row 2 and column 3 deleted. Well, here's row 2, here's column 3, so we take this row out and this column, and we get this matrix. Notice that A is 4 by 4 and A23 is 3 by 3. So in general, a submatrix is going to have one less row and one less column than the original matrix. So here's the definition of determinant. Given an n by n matrix A where n is greater than or equal to 2, we'll see down here what do you do when n is equal to 1. But when n is greater than or equal to 2, the determinant of A, which is written using this notation, either det with A in parentheses or the matrix A with vertical bars on either side, the determinant is given by this definition. This is a pretty complicated looking definition. One of the first things that we can notice is that the determinant of A is defined in terms of other determinants, in particular, the determinant of submatrices, in this case A1j. Then it's got this minus 1 to the 1 plus j power here. This is an alternator. If you've had Calc 2, you may remember those. And then this is the entry in matrix A in position 1j in row 1, column j. Since this is kind of complicated, instead of explaining exactly what this looks like, we'll do some examples. And then here we'll say if n is equal to 1, the determinant of A, which would be a 1 by 1 matrix, so that's really just a number. The determinant of a 1 by 1 matrix is just the number in that 1 by 1 matrix. Remember, this notation means the entry in matrix A in row 1, column 1, and if it's a 1 by 1 matrix, that's the only entry in the matrix. So the determinant is just equal to the number in the matrix. Before we do an example, it will be useful to see this theorem about the determinant of a 2 by 2 matrix. So if A is a 2 by 2 matrix, written A, B, C, D here, so remember the vertical bars means the determinant of this matrix. So the determinant of this 2 by 2 matrix is just A times D minus B times C. And we can use the definition up here to see where this comes from. So we let J go from 1 to n. Well, n is 2 in this case because this is a 2 by 2 matrix. So we're going to have two terms here. J is going to go from 1 to 2. We'll have minus 1 to the 1 plus 1 power. So that's minus 1 squared, so that's positive 1, times the entry in row 1, column 1. So J is a 1 here. So the entry in row 1, column 1 is A. So we've got 1 times A times the determinant of the submatrix A1, 1. So that's the matrix we get when we take out the first row and the first column. Well, that just leaves D. So that's times the determinant of D, or the matrix that just contains D. And then we let J increment to 2. So we have minus 1 raised to the 1 plus 2 power. Well, that's minus 1 cubed, which is negative. So we get plus a negative, which is where the minus sign comes from. And then we have the entry in matrix A, row 1, column 2. So row 1, column 2. So that's a B. So that's where the B comes from, times the determinant of the submatrix A1, 2. So we take out row 1, column 2. And we're just left with C and a 1 by 1 matrix with just a C in it, and we have the determinant of C. Based on our definition up here, the determinant of a 1 by 1 matrix is just the entry in that matrix. The determinant of D is just D. The determinant of C is just C, and so we get AD minus BC, which is the formula. Of course, when we use this theorem, we don't think about this definition. We just think multiply A times D and then subtract B times C. So you multiply across and then multiply across and subtract. Okay, so now let's see an example. Here's a 3 by 3 matrix and we want to compute the determinant. And I know it's a determinant because it's got these vertical bars instead of the square brackets. Okay, instead of trying to explain how the definition applies to this matrix, I'm just going to show you in practice how I apply the definition, and you can go through and convince yourself that this actually is what the definition does. The first thing I'm going to do is put an overlay of signs to take care of that alternator. So the alternator changes sign. We start with the first entry in row 1, and the alternator is going to be positive. It's going to be -1 squared. And then as I increment j and move across the first row, then I'm going to alternate signs. So positive, negative, positive, and if I had more entries in the first row, I just keep changing sign. Positive, negative, positive, negative, positive, negative, etc. So that takes care of the alternator term. And then I just multiply by each entry in the first row the corresponding submatrix when I take out the row and column that the entry is in. So for the 2 here, the submatrix I need is the one where I take out the row and the column that the 2 is in. So I sometimes just cross out the column and the row, and that leaves me these 4 entries, -3, 3, 2, -2. So I've got 2 times the determinant of the submatrix that's left when I take out the row and the column that the 2 is in. And then -0 times the submatrix that I get when I take out the row and the column that the 0 is in. So I'm still taking out row 1, but now I'm taking out column 2. So I get 5, 3, 1, -2 in my submatrix. And I take the determinant of that. Now, of course, since I'm multiplying by 0, I could just skip this step. Whenever you see a 0 in the row that you're going across, you can just leave that one out. You have to make sure that you still follow the pattern of the signs, but you could leave out that 0 term. I just included it to make this example very clear. Then I get plus -1. So plus -1 times the 2 by 2 determinant I get when I take out the row and the column that the -1 is in. So take out the first row and the third column, and I get this 2 by 2, 5 -3, 1, 2. And then for the 2 by 2s, I use the theorem that we just proved. So to calculate the determinant of this 2 by 2, I multiply -3 times -2, and then subtract 2 times 3. So this is the determinant of my first 2 by 2. The 0, I'm not going to bother doing the determinant of this 2 by 2 because I'm going to end up multiplying by 0. So I just said -0 here. Then I've got plus -1, so we'll say minus the determinant of this 2 by 2. So I multiply 5 times 2, and then subtract 1 times -3, and then just do the arithmetic and simplify, and we get -13. Notice that the determinant of a matrix is a number. So you can think of the determinant really as a function, and it takes as its input a square matrix. Remember, in the definition, the determinant is only defined for an n by n, or a square matrix. So we can't have the determinant of a 3 by 5 or a 4 by 2 matrix. Determinants are only defined for square matrices. So the input is a square matrix, and the output is a number. And it doesn't matter what size the matrix is, 3 by 3, 3000 by 3000, the output is always a number. All right, if we look at what we just did here, I computed the determinant of a 3 by 3 matrix, and in order to do that, I had to compute 3 2 by 2 matrices. That's because of the recursive nature of the definition. If we go back and look at the definition here, the determinant of A is the sum of some terms that include the determinants of A1j. So if A is 5 by 5, these determinants will be 4 by 4s. Well, how do you evaluate these 4 by 4s? You use this definition again. So for each of these 4 by 4s, you'll use this definition, and the determinant of A11 here will be the sum as j goes from 1 to 3 of a bunch of terms that include the determinants of 3 by 3s, and each of those 3 by 3s will be done using this definition with a bunch of terms that include the determinant of 2 by 2s. So here, with a 3 by 3, we do 3 2x2 determinants. With a 4x4, I'd have to do 4 3x3s, and with each of those 3x3s, I'd have to do 3 2x2s. Well, this can add up pretty quickly. You can figure out without too much trouble, if you think about it, that it takes a total of n factorial over 2 2x2 determinants to compute the determinant of an n by n matrix. Remember, n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So let's see how many 2x2 determinants we would need to compute for various size matrices. For a 3x3, as we just saw, we would need to compute 3 factorial, which is 6, divided by 2, or 3 total 2x2s. That's not bad at all. For a 4x4 determinant, well, 4 factorial is 24. 4 times 3 times 2. Divided by 2, that's 12. So we go from 3 to 12. We increase the size of the matrix by 1 from 3x3 to 4x4. We quadruple the number of 2x2 determinants that we need to do. So this is not looking good. A 5x5 determinant will require 60 2x2s. A 6x6 will require 360. And if we jump up to a 10x10, which is a small matrix by modern standards, it requires 1.8 million 2x2 determinants. This is too many. This is too many to do, certainly by hand, and even on a computer, this could take some serious time. If n is 100 by 100, which is relatively small for a lot of modern applications, well, 100 factorial is about 9 times 10 to the 157. So half of that, 4.5 times 10 to the 157. That's how many 2x2 determinants we would have to do. Well, that number is literally incomprehensible. According to some physicists, there are about 3 times 10 to the 80 particles in the entire known universe, elementary particles. 10 to the 157 is almost 2 times as many orders of magnitude. So an order of magnitude is a power of 10. So 2 times 80 is 160. So 157 is almost 160. This definition that we use to compute determinants requires way too many computations. So we need to do something else in order to be able to compute determinants from a practical perspective. So we have some theorems that will help us out with that. The first one says that the determinant of an n by n matrix can be computed by expanding across any row or down any column. What I mean by expanding across any row is, in the definition, we go across row 1, but we could go across row 2 or 3 or 4. We could also go down column 1, column 2, column 3, or column 4. I left the proof out. You can read the proof in the book. It's a little bit involved in terms of sigma notation and etc. The important thing for us is the result. So I'll do this example taking advantage of this theorem. Now notice if I went across row 1, which is in the definition, I have a 0 here, so I don't have to worry about this term, but I'm going to have 3 other determinants I'll have to do. And since this is a 4x4, each number here is going to be multiplied by a 3x3, and each of those 3x3s will be multiplied by a 2x2. But if I look down here, row 3 has 3 zeros. And so if I were to go across row 3 instead of across row 1, I'll get 3 terms that are 0, and I only have to do a single 3x3 determinant. Likewise, if I were to go down column 3, same thing. I have 3 zeros and only 1 non-zero term. So in general, when you're faced with doing a determinant, particularly by hand, look for zeros. Zeros make the determinant easy, and find the row or column with the most zeros. In this case, column 3 and row 3 have the same number of zeros, so it doesn't matter which one we pick. We're still going to have the same number of computations. And just to illustrate that it works and that we get the same answer, I'll do both ways. So if we go down column 3, expanding down column 3, well, the first thing we have to do is get our overlay of signs down column 3. And we do that the same way that we did before. We always start at the top left with a plus, and then every time you move left or right or up or down, you just change signs. So I want to get over to column 3 and then go down. So I do plus, minus, plus, and then down column 3. This is a plus, so minus, plus, minus. And so the 3 here is going to get multiplied by -1. The zeros, I don't even have to worry about. So that's where the -3 here comes from. So the determinant of this matrix is equal to -3, the -3, times the 3x3 determinant that's left when I take out the row and the column that the 3 is in. So the 3 is in row 2, column 3. So this is submatrix A 2, 3. So I have minus 1, 3, 7, 0, 1, 0, 2, 8, minus 2. And then, to do this 3 by 3 determinant, I need to pick a row or a column to expand across. Well, there are 2 zeros in row 2, so I like that one. I got 1 0 in column 1 and 1 0 in column 3, none in rows 1 and 3 or column 2. So the row or column with the most zeros is row 2 that has 2 zeros. So I'm going to go across row 2. Well, I need to do the pattern of signs. So that's plus, and then I want to go across row 2. So I'm just going to start from here and go down to row 2 and then go across. So positive, negative, positive, negative. And I can see the non-zero entry has a positive sign. So I'm going to do positive 1 times the 2 by 2 I get when I take out row 2 and column 2. So minus 1, 7, 2, minus 2. Notice the minus 3 is here from before. And now I have the 1 from expanding across row 2 here. And to do the 2 by 2 determinant, as before, I just multiply across minus 1 times minus 2, and then subtract 2 times 7, do the arithmetic, and I get 36. Okay, so let's do this again, and we'll expand across row 3. Well, I need to get my overlay of signs for row 3 now. So here's my overlay of signs for row 3. Starting, as always, at the top left, I'm going to go down to row 3 and then across. So positive, negative, positive, negative, positive, negative. Notice that this 0 already was marked as positive when I came across and down column 3. And it doesn't matter what path I take to get to this 0 is always going to be positive. This 1 is always going to be negative. We could figure out this minus 2 would have a positive sign, etc. So it's a nice thing about the pattern of signs. It doesn't matter what path you take. You could figure out what sign every entry in the matrix would have for the alternator in the determinant, and it's always going to be the same no matter what path you take. Okay, so going across row 3, I see that the only non-zero entry, the 1, is going to get a minus sign. So that gives me the minus 1 here. And then I look at the submatrix I get when I take out the row and the column that 1 is in. So I'll have minus 1, 0, 7, 5, 3, minus 4, 2, 0, minus 2. And then in this 3 by 3, I look for the row or column with the most zeros. That's column 2. So now I'm going to go down column 2, so I get my overlay of signs, starting as always in the top left, changing signs every step I take, positive, negative, positive, negative. So the 3 is going to have a positive sign, so I'll have minus 1 times positive 3 times the 2 by 2 I get when I take out the row and the column that the 3 is in. So minus 1, 7, 2 minus 2, and then to do the 2 by 2 determinant, I multiply across, minus 1 times minus 2, minus 2 times 7, then do the arithmetic, and I get 36. And of course, it's the same answer that I got up here. And for fun, we could expand across a different row or a different column, and every time we did that across any row or column, we would always get 36. That's what this theorem tells us. This isn't a proof, this is just an example, but this example illustrates the theorem, which can reduce the number of computations that we have to do pretty dramatically. Notice that in both of these examples, I only had to do 2 determinants. Normally, as we saw earlier, a 4 by 4 matrix would require 12 determinants. But because I chose wisely which column or row I was going to expand across, I was able to minimize the number of determinants. In this case, I only had to do 2. All right, so there are some more properties of determinants that help simplify the computations. Before we get to those, we need to define a couple of things. First, we'll define an upper triangular matrix to be an n by n matrix that has the following form. The main diagonal here from top left to bottom right can be any numbers. So A11, A22, these can be any complex numbers, 0, non-zero, anything. The top right here, the asterisk, means these numbers can also be anything. And the big 0 down here in this bottom triangle means that all these numbers down here have to be zeros. So everything below A11 in column 1 has to be a 0. This is the A22 is the entry in row 2, column 2. So row 1, column 2 can be anything. Row 2, column 2 can be anything, but everything below A22 has to be a 0. Everything below A33 has to be a 0, etc. This is upper triangular. Lower triangular is the reverse. You can have anything on the lower triangle, and the upper triangle has to be all zeros. These entries here are called the upper triangle. So everything to the right and above the main diagonal is the upper triangle. Everything to the left and below the main diagonal is the lower triangle. Same thing down here. So an upper triangular matrix has any entries you want. These numbers can be anything. The upper triangle can be anything, but the lower triangle is all zeros. So it's a little bit counterintuitive. Upper triangular means the lower triangle has to be all zeros. Lower triangular means the upper triangle has to be all zeros. Okay, so now we have another theorem. If A is an n by n matrix, and if it's triangular, either upper or lower triangular, then the determinant is just the product of the diagonal entries. So this notation, the capital pi, as I goes from 1 to n, it's similar to the sigma notation that we use to add things up, but the capital pi is used for the product, so we multiply these together. So we could write it out like this. Expanding this notation, it's A11 times A22 times A33 times A44, etc., up to times ANN. The proof is pretty straightforward, and it relies on the previous theorem that says that we can expand across any row or down any column. So if I have an upper triangular matrix here, where the lower triangle is all zeros, I'm going to expand down column 1. Now remember, everything below A11 is a 0. So when I expand down column 1, I'm going to get A11 times the n minus 1 by n minus 1 determinant I get when I take out row 1 and column 1. So that's here. And then minus 0 times some other determinant plus 0 times some other. But I'm multiplying all those other determinants by zeros. So I really only have to do one determinant if I expand down column 1. So this determinant is equal to this one. And then notice what this is. This is another upper triangular matrix. And to do the determinant of this one, I'm going to expand down column 1 of this matrix, which also has all zeros underneath A22. So it'll be A22 times the determinant of the submatrix I get when I take out row 1 and column 1 here. We can see that one here. And so I've got A11 times A22. And since the overlay of signs always starts with a positive on the top left here, I'm going to have positive A11, positive A22, or more strictly speaking, a positive 1 times A11 and a positive 1 times A22. So if either of these numbers are negative, then they'll be negative here. And I can just keep doing this. All zeros under A33, so I'll get A33 times the matrix that's left when I take out row 1 and column 1 of this matrix. So that's going to leave A44 at the top, and then I'll have A44 times another submatrix, etc., until I get down to just a 2 by 2 matrix. And that's going to be a n minus 2, n minus 2 times a n minus 1, n minus 1, and then a n n. This could be anything. It's an asterisk here, but this is a 0. Well, how do I compute this 2 by 2? I multiply across and then subtract the product here. Well, 0 times whatever is 0. So I really just have to multiply these two together, which I get here. And what we have here is the product of all of the original diagonal entries. So A11, A22, A33, all the way to ANN. And that's the formula that the theorem claims is equal to the determinant of A. If A is lower triangular, just swap the 0 and the asterisks in the matrices and expand across row 1 instead of column 1, and then expand across the first row of every subsequent submatrix, and the equations will be all the same, and the result will be the same. Okay, another thing that's really helpful is to know how row operations on matrices affect determinants. So again, this is another theorem without proof. There's a proof in the book. If A is an n by n matrix, if we do any of the 3 row operations, the determinant is affected in the following ways. So if we do the first row operation, multiply a row of A and add it to another to produce a second matrix B, amazingly, it doesn't change the determinant. So the determinant of the new matrix B is equal to the determinant of the original matrix A. If we swap two rows of A to produce a matrix B, then the determinant of B is equal to the opposite of the determinant of A. And if we were to do this twice, well then obviously two negatives gives us a positive, so we would get back to just the determinant of A. If I do the row operation of multiplying a row by a scalar, alpha, to produce B, the determinant of B is equal to that scalar alpha times the determinant of A. If we summarize this, any row operation will affect the determinant of a matrix in a very limited way. This row operation doesn't affect it at all. This row operation changes the sign, and this row operation can scale it by a non-zero scalar. Remember, you cannot multiply both sides of an equation by 0 when you're solving an equation. So the row operation, where we multiply a row by a scalar, also excludes 0, and that'll be important later. This alpha here cannot be 0. Okay, then the next theorem says if A is an n by n matrix, it's invertible if and only if the determinant of A is not equal to 0. Well, we're going to add this to the invertible matrix theorem. In fact, we already did. You might have noticed that I snuck this equation into the invertible matrix theorem in one of the previous videos. A matrix A is invertible if and only if its determinant is not 0. The proof is pretty straightforward. I won't go through the details for the sake of time. I'll just point out that this is an if and only if statement. So we have to prove both directions. We have to prove if A is invertible, then the determinant of A is not equal to 0. We also have to prove if the determinant of A is not equal to 0, then A is invertible. Then we have the theorem that says if A is an n by n matrix, the determinant of A transpose is equal to the determinant of A. And that is a simple result of the theorem that says we can expand across or down any row. Row 1 of A transpose is the same as column 1 of A. So if I expand across row 1 of A transpose, I'll get the same thing as if I were to expand down column 1 of A. And then finally, the last theorem says that if A and B are both n by n, the determinant of their product is the product of the determinants. I left the proof out here. You can read the proof in the book. It involves elementary matrices, but really the only time we'll ever need elementary matrices in the course is to prove this theorem. So I didn't include them in these notes for the sake of time. All right, that finishes our video on determinants. We defined and did some examples of computing determinants, and then we proved some theorems, which will be useful later when we are evaluating determinants and proving other theorems about them.